Hey students. All right, so next section is on making graphs and making tables for descriptive statistics. All right, so first, let's describe the idea of a distribution. When we're talking about random variables, there's a couple things that we should keep track of. There is what values a random variable could take, and there's also how frequently those values are taken. Those ideas are captured in the distribution of the data set. So in this section, we're going to see some basic ways to understand a distribution of an observed data set, and in later sections, we're going to talk about the idea of the distribution of a population and how it could possibly extend the idea of distribution. And one basic way that we could understand a distribution is using a table, and we can also use visualizations. Visualizations can actually be very helpful in understanding a distribution because there are things that our eyes are very good at picking out. And when we make pictures of our data set, we pick those things out. Like, for example, where does the data tend to cluster? How spread out is the data? Are there outliers in the data set? Influential observations. And our eyes are actually very good at noticing those features. So, creating visualizations of data sets can lead to us learning a lot that actually really cannot be learned by numbers on their own. In fact, there are some examples. For example, there's this thing known as Anscombe's quartet. Maybe I should very quickly have a look at Anscombe's quartet, because we can do that very quick. Okay, so let's see. WK Anscombe. Is it B? Quartet. This is close enough. It'll probably figure it out. Is it Anscombe? I can't type. Oh, okay. So it has a B in it. All right. So there's this picture right here, and this is known as Anscombe's quartet. This is for a bivariate data set, which is not what we're talking about right now. But when working with bivariate data sets, you want to track, for example, the mean of X and the mean of Y, and also if you were to come up with a best fitting line, a regression line between the two variables, what would the parameters of that line be, and what is the correlation between the variables? And numerically, every single one of these data sets are exactly the same. Even though our eyes can see they are not the same at all. These are clearly not the same data set, and they have very different properties. So making visualizations can help us learn a lot. In fact, this is a subject in and of itself. You can take a class from the computer science department on just visualization. But we're not going to be going into that much depth in visualization today. What we learned today is pretty much enough to get you by in life, unless you're doing some really serious work. So from this point on, in this video and future videos, I use this notation to describe a data set. And this data set has sample size n. So the sample size is the number of observations in a data set. The indexing here, we have x1, x2, xn. The indexing, the numbers themselves don't actually matter. They're just a way for us to differentiate observations. These observations may have the same values or different values. It actually doesn't really say all that much about the data set. In particular, I don't want you to look at this and think that this data set is now ordered. This data set is not assumed to be ordered. If the data set ever becomes ordered, I will let you know. But right now it isn't. I also would like to draw attention to the fact that this is in lowercase, and it's not a perfect rule. I've often violated it, but it is a hint that lowercase things, and this will probably be the case in the videos for this class. It is generally the case that lowercase numbers are constant. And a data set is constant. A data set is something that you observe, and because you observed it, it is now constant. Whereas capitals often refer to random things, which is not what we're going to talk about today. So the first visualization method that we're going to talk about is very basic. It's called a stem and leaf plot. So we create a stem and leaf plot using the following steps. The first thing we are going to do, given a data set, is we're going to select the number of leading digits to be the stem values. So we have a number, maybe that number is 123.45, and we're going to select some number of digits, maybe the first 2 digits, and these will be the stem values. The remaining values, let's use a different color for that. Where did red go? The remaining values will be the leaf values, which in principle you could put like the entire block 345 as a leaf value, although a lot of people will just like round to just 1 digit because, well, you'll see for a second why someone might be inclined to do that. So after you make that selection, you're going to draw a vertical line. Let's not use that color. We're going to draw a vertical line, and we're going to list the stem or possible stem values on the left-hand side of this line. So we might have 12, 11, 10, and maybe 13, and 14. And on the right-hand side of this line, we would record the leaf values. Let's assume for a second, just for simplicity, that we didn't observe this part, and all we saw was the 3. We might list 1, 2, 3, and this would be read off as 123. Because according to part 4, we're somewhere in this display, we're going to indicate the units of the stem. So we might say, in this case, tens, to indicate that the stem is tens place and beyond, which means that everything to the right will be in the ones place. Or maybe we're doing a more advanced plot where maybe we actually did write 3, 4, 5. So this would be 1, 2, 3.45. But we're not going to do that because I actually think that would be... It kind of defeats the purpose of a stem and leaf plot, because what we would instead do is list the leaf values for each observation or data set. So maybe you saw 101, 111, 2, 3, 4. So we have an observation 114 and another observation that's 113 and another observation that's 112. Or we'll also even throw in a 9. So there's an observation that's 119. We got 123, 130, and 144. And now we have a display. Let's just throw in like one more number, like right here. Now we have a display that actually later on we're going to see a histogram and say, oh, this actually looks a lot like a histogram. But we do have this display that's indicating that's telling us a lot about this data set. For one thing, it actually tells us the actual values in the data set. That's one advantage of a stem and leaf plot. When you have a stem and leaf plot, you get to see the actual data values, and that's one thing that's nice. Another thing that's nice about them is that they're very quick to create. Like, I imagine a stem and leaf plot being created in the field. Like, you are out there, you are watching, birds and tracking how many birds you're seeing or characteristics of birds, and you actually get to write down, as you are recording your data, you're also visualizing it so you can learn things about it, because you can see, like, for example, this data set seems to cluster in this 100 and 110s area. We might be able to guess that the mean is somewhere around here, that this is like where the center of the data set is, and we get some sense of its spread. All right, so here is another data set for us to practice with. This is a subset of McDonald's data on height and finger lengths, and this part right here is actually R code. So we could go into R and type this part in and use R to do some of this analysis. So, and I'll actually show you a little later how this can get turned into, like what R would do with this part. But we're just going to take this and treat it as our data set and construct a stem and leaf plot by hand. So what are we going to do? we first need to decide where we're going to make the cutoff. We're not going to make it in the ones place, because if we put it in the ones place, then there's going to be just 5 for our stem value. And what you'll end up with is a plot that looks like this, and it will be just like a giant skyscraper, and you won't learn anything. So we don't want that. So the next place that is available to us is the 10th place, and the 10th place seems pretty good. So I'm now going to make the line for the stem, and I'm going to write, let's see, we've got 5 3 5 5. We have a 5 2. We also have a 5 0. So we'll put 5 0 5 1 5 2 5 3 5 4, and we go all the way up to 5 9. So 5 5 5 6 5 7 5 8 5 9. Okay, there's some dead spots on this super cheap computer. I bought it for $200 at Target across the street, which was the most convenient place to buy a laptop super cheap. So you get what you pay for, and I'm especially learning that right now. Anyway, so we now have the stem values, and now we can start recording our data set. If you were to do this in a computer would actually order the leaf values. Here they actually are ordered because 9 comes after 4, which comes after 3. So a computer would actually order it. I don't really see the point, because the point is to understand the distribution as in a visual way, and ordering the leaves does not aid in that. So we can go ahead and just start reading across in this data set to make our stem and leaf plot. So we've got 5.55, so we'll put a 5 right here. 5.30, so we'll put a 0 there. 563, 530, 513, 505, 538, 596, 521, and 538. So in this case, it actually turned out to be ordered, and that's pure coincidence. I wasn't planning on that. But now we have a stem and leaf plot. And if we scroll down, or if you actually have these notes printed out, one last thing we need to do is indicate what this line means. And this line is the 10th place. Okay. All right, so if we were to continue on to the next page, we would actually see some R code that would do this. So this is the height data set from before, this part right here, the R function. Oh, okay. So this is the same height data set we had before. The R function stem creates stem and leaf plots, and this is basically the same as we had before. Okay, before I continue on, I'm just going to double check to make sure I'm still streaming. Yeah, we're still streaming. Okay. All right. Okay. So next up for our visualizations, we have a dot plot. A dot plot represents each data point as a dot along a real number line. So we would then be looking for clusters in dots to note patterns in our data set. So in this example, we're going to use the data from the previous example, which has already been very nicely organized for us in a stem and leaf plot to create a dot plot. Let's see. Is there a nice, easy way to zoom out? Oh, very nice. Oh, that's not what I wanted. That's delete. I'm new to this program. And we're at the very bottom too. That's not what I want either. Okay, so all right. So this program is new to me. My apologies. All right. So all I want to do is zoom out a little bit. Okay, that's good. That's good. Oh, cool. All right. I just want to be able to see this nice stem and leaf plot that we created before. when creating our dot plot. So for our dot plot, let's see. We've got, let's see. So for the left point of the range, we should pick 5.0. And for the right point of the range, we should probably pick 6.0 because we get really close to 6. So in between, we've got 5.5. And then we can just mark off in fifths. So 1, 2, 3, 4, 5. Okay, that's close enough. If you want perfection, ask a computer to do it. All right, so we've got an observation 5.05. So that's about right there. 5.13 is about there. 5.21 is about there. And then we've got 5.30. That is about there. And that's also got another one right with it. There's another observation. That's actually could be a little bit to the left, but we could also call that 5.38. So here's 5.30 for realsies this time. We've got 5.55, 5.63, and then 5.96. So then we end up with this dot plot. That's also giving us a sense of where the data tends to lie, but this time along a real number line. So, and I'm sure you can guess so far that the methods that we have been working with, our visualization methods, are pretty much devoted exclusively to quantitative data. We'll see categorical in a second. I'm pretty much going to say draw a bar plot, and that's it. So here is our code for what I just did. The R function for making dot plots is strip chart. So strip chart is what makes these things, and I'm just passing some additional parameters to strip chart to make the function to make the plot how I like. Like for example, this parameter right here controls how what exactly we're drawing here. Are we drawing filled in circles or empty circles and so on? So this, you can think of this as point character because you're choosing the character of the point, and 19 corresponds to a filled in circle. We have a little bit of an offset and some other parameters that just help make the visualization look nice. I would recommend going ahead, firing up R, playing around with these parameters, seeing what happens. Stack, for example, means that when 2 points are about to collide with one another, stack them on top of each other. Because it's not the only way to do things. There are often very many ways to solve the same problem. So, all right. Continuing on. So a quantitative variable, we need a further refinement of quantitative variables, and we say that a quantitative variable is discrete if its possible values are countable. Countable, that could be, for example, 1, 2, 3, 4, 5, 6, or that could be 1, 2, 3, 4, 5, 6, 7, 8, 9, blah, 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 up into the future. It could be the integers, so including negative numbers as well, or including 0 as well. And then, so we would call any of those things countable. There's also continuous variables, where the possible values could come from a continuum, so that includes 0, 1, and anything in between. So 0, 1, 0.5, 0.011012, 1 divided by pi, any one of those things are possible. There's actually a nice little rule of thumb, which is that discrete variables emerge when you count things. Like, for example, I count sheep. So what am I going to get? I'm going to get an integer in the end. So if that's going to be the case, then it's countable. Whereas continuous emerges from measurements. So like with a ruler. So you measure how long something is with a ruler, and that will probably produce a continuous variable. So continuing on, some further notions when describing a distribution. There is the frequency of a value, and there's also the possible values it could take. So the frequency is how frequently we see a variable take a particular value. And for discrete variables, it is in fact possible and quite likely that we will see the same numbers repeatedly. Whereas if we're dealing with continuous, you cannot necessarily assume that. So the frequency for each value for a continuous variable would be rather uninteresting, since you're probably going to see, like going back to the data set we were just looking at, admittedly, for this height data set, we did have some collisions, but you can't really count on that. You can imagine that if you were to increase the decimal precision of the numbers that you're looking at, you would actually not have a collision. You'd have two distinct numbers. The only reason why we get 5.30 twice is because that's where we decided to round. So in the case of continuous variables, while with with discrete variables, it's okay to just kind of consider the values in and of themselves and just say, how many times did 1 show up, how many times did 2 show up, and so on. For continuous variables, we probably should do a procedure known as binning. So binning is where we define a range in which a data point could possibly be, and instead of tracking how frequently a certain value is taken, we're going to track how frequently a variable will fall into a bin, right? So you can imagine, for instance, that this is a continuous line between 0 and 1, and we saw numbers in this region, and they're just random numbers, and we're not going to actually list out in a table how often we saw those individual numbers, because most of the time the frequency for that number will be 1. Instead, what we'll do is we'll divide up this region and then count how many times numbers fell into those individual bins. Like, for example, we got twice here, 3 times here, 1, 2, 3, 4, 5, 6 times here, 1, 2, 3, 4, 5, 6 times here, and then 4 times here. And then we'd have like a more useful table for understanding our distribution. Very closely related to the frequency is the relative frequency. Relative frequency is where you take the frequency and divide it by the sample size. That's it. So if you really want to see a formula for the relative frequency is equal to frequency divided by n. A frequency distribution is a tabulation of the frequencies or the relative frequencies, or in the case of continuous variables, we'd probably also include the frequency of bins. Something that I haven't really discussed so far is that actually, how should we choose the bins? Like binning is a choice. I chose these bins, but alternatively, I could have chosen bins like this. Like, here's one bin and here's another bin. Why didn't I do that? So the actual binning decision is in fact a decision. You need to decide how many bins they are and what regions they're going to cover. So in terms of the regions, I think it's pretty safe to say the bins should be equal length. If the bins are not equal length, then what you're going to end up with is a difficult to understand chart or a difficult to understand table, because people then have to pay much more attention to the bin length. And also when you're trying to visualize what's like this is leading up to histograms, and the bin size is something you have to make when talking about histograms. And when you end up with bins of unequal length, then the histogram, there is a precise way to understand what's being visualized in the histogram, but unfortunately, people's eyes are not going to perceive it that way. And you are making the histogram more difficult to understand. So just always make your bins equal length. But the number of bins that you have, and also what exact regions they cover, because you can still, for example, take all of these bins shown here, take all of these bins and then shift them slightly to the left, and then you have a different visualization, or you then have a very different description of your data set. How exactly should you decide where the boundaries of your bins are, and how many bins should you have? These are all very important decisions that can have drastic implications for visualizations, but I really should move on to actually creating a frequency distribution, which is a tabulation of frequencies or relative frequencies. I should really move on before I start digging into that topic. So let's make a frequency distribution for this soccer data set where we have a supposed statistically minded parent. Maybe that parent is you if you have a daughter or a son and they play soccer, and you've decided that you're going to track their little league soccer team scores during a regular season. So here I have a data set. And by the way, what I've done here in terms of R code is created an R vector. So I have this list of values in what's known as an R vector. I'm not really going to talk about R in these videos. I'm going to pretend and assume that you are watching my video series on how to use R. But enough of that for now. I want to construct a frequency distribution for this data set. So what are possible values in this data set? Let's see. So on the left-hand side of this line for this table, so we're going to have a value, and we're going to have on the right-hand side the frequency. So what are possible values? Well, we've got 1, and we've got 9, and we've got numbers in between. So we'll just go 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, and then we need frequency. So let's see. How many times did 9 appear? Looks like 9 just appeared once. All right, so we got that covered. 6 appeared. So 1, 2. Yeah, that's it. So 6 appeared twice. 5 appeared 3 times. And 8 appeared twice. And each of the remaining numbers appears only once. So 1 appeared once, 2 appeared once, 3 appeared once, and 4 appeared once. Okay? 7 never appeared. All right. 1 second. I catch up in my notes. So the sample size for this data set, you can count. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 observations. Or alternatively, what you could have done is, and in fact, I'll go ahead and just kind of scroll down a little bit. And down here, I'm going to track the sum. And yeah, it adds up to 12. Another thing I want to do is, in this table, track the relative frequency. So we'll call this relative frequency. And in the relative frequency, I'm going to take the frequency and then divide by the sample size. So 1 divided by 12, that is going to be 0.05, or is that an 8? No, that's an 8. 0.083, and the 3 is a continuing digit. All right, so for the next one, it's the same thing, 0.83. And again, for 3, 0.083. Okay, and then for 5, no, wait, so let's see. 4 also appeared that amount, so 0.083. 4 appeared 3 times. So that's going to be 0.25. Because 3 divided by 12 will be 0.25. 3 is a quarter of 12. 6 will be 0.16, where the 6 is a continuing digit. 0.16. And 0.083. Okay, and if you add these numbers up, this is a way for you to check your sanity. This should add up to 1. Okay. So moving on, if you were interested in how to make a table like this in R, the function for R, in R for making such a table is, well, table. So you would have given it the soccer data set and asked it to make a table, and it will tabulate which observations were taken and how frequently they were taken. Notice that it did skip 7, which, I don't know, is that a feature you want? I don't know. I actually personally would rather not skip 7, and you'll probably see why in a second. When working with continuous data, as I was mentioning before, there's this issue of binning, deciding on the number of bins, deciding where the boundaries of the bins are, and so forth. But once you've decided on the number of bins, and there are some rules of thumb that you can use for how many bins that you should use. Like, for example, if the sample size is n, you could perhaps choose the number of bins to be the square root of n. Actually, there is some statistical arguments that the correct number of bins should be on the order of n to the power 1/5, or the fifth root of n. There are some arguments for that, but square root of n is also fine for now. At the end of the day, whatever it is that R is going to use for its binning decisions is better than what you're going to do. And it's going to have some nice theory backing it up. So you probably should just trust R. Whatever R is doing is probably better than the square root of n rule. So after you've decided on the number of bins, you segment your number line so that you have that many equal length bins. And depending on where each data point falls, assign it to a bin. If it falls on a border between the bins, assign it to the bin on the right. So, in other words, bins are right inclusive. That is a parameter. Some people prefer left inclusive bins. Does it really matter? No, it doesn't. It doesn't really matter. Nobody really cares. Just pick one, right? And be consistent. Either put it on the left bin or the right bin. Just don't put it in both, please. And then construct a frequency distribution for the bins. Very quickly before I keep going. Okay, we're still good. All right. I'm very nervous about losing this video. I'll just put it this way. Today I've recorded a number of videos that suddenly just went up into thin air because things went bad, and I don't want that to happen again. All right. So example 4. So using the data from example 1, you can go back in time to see what that is. This is the heights data set. Construct a frequency distribution. And for what it's worth, there were 10 observations in that data set. The function length, when given a vector, will tell you the number of elements in that vector in R. So since the number of elements is the number of data points, we want to use length to determine the sample size. Okay. Continuing on, I have made some decisions. I'm going to decide that the number of bins I'm going to use is going to be about the square root of 10. The square root of 10 is between 3 and 4. So if you wanted to use the square root of 10 rule, that would be about, we'll say 4, rounding up. Although, apparently in my notes, I decided that I was going to go with 5. And I don't want to change it. So I'm going to go with 5. Why 5? Why not 5? It's whatever you want. I think the reason why I went with 5, I don't know. I just did. So, let's go ahead and zoom. Oops, is that what I want? Yeah, that's fine. Okay. So, I'm going to make a table. So in this table, I'm going to list the bins. So I've got 5 to 5.2. And to indicate that this is going to be right inclusive, I'm going to put a little less than sign to say 5 to less than 5.2, not including 5.2. And then 5.2 to 5.4, 5.4, hold on. Okay, 5.4 to 5.6, 5. I need to kind of get away from there. Okay, 5.6 to 5.8, and then 5.8 to less than 6, and we can just leave it at that. All right, and then we have the frequency for each of these bins. So the frequency for these is going to be, well, there were 2 numbers between 5 and 5.2, 5 numbers between 5.2 and 5.4, and then 1 number in each of the remaining bins. So if we were to do the relative frequency, we're going to take each of those frequencies and divide it by 10, in which case you're just going to move the decimal point over one place. So 0.2, 0.5, 0.1, 0.1, 0.1. Okay? All right. Once we have a frequency distribution such as this, we can now construct what's known as a histogram, which is a plot for visualizing the distribution of quantitative data. So how do we construct a histogram? First, draw a number line and mark the location of the bins. So for example, we could do something like this, and we're going to say that the bins are going to be about here. And then if you want to, for discrete data, you can center your bins on the corresponding values themselves, because you're not really doing any binning with the discrete variables. Or you can imagine that your bins are exactly what they need to be touching each other and centered on the integer, the corresponding integer. And then for each of these classes or bins, draw a bar extending from the number line. So we have some y-axis that's tracking, let's say, the frequency. So we have a y-axis that's tracking the frequency. We're going to draw a bar from the number line to the y value that corresponds to the frequency of that bin, or the relative frequency if that is in fact what you're plotting on the y-axis. So we would end up with a plot maybe looking like this, and that resulting plot is a histogram. Okay, so going back to some of our examples, let's draw a histogram for the data set in example 3, which was that soccer data set. So for the soccer data set, we had numbers between 1 through 9. We'll go ahead and include 0 as well for this data set. So I'm going to start out by drawing the graph. The x-axis corresponds to goals, so goals in a game, and the y-axis corresponds to the frequency. So let's see. The frequencies never seem to go beyond 3. So we've got 1, 2, 3. Okay, and then possible integer values. I'm going to go ahead and include 0 because in principle this soccer team could score 0 points. So we'll go ahead and include 0, but we'll also include at the very end we'll have 9, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there was one game where they scored 1 point, one game where they scored 2 points, one game where they scored 3 points, and one game where they scored 4 points. Then they had 3 games where the team scored 5 points, 2 games where they scored 6 points, no games where they scored 7 points, 2 games where they scored 8 points, and 1 game where they scored 9 points. Okay. New feature. Let's go ahead and see what happens when No, I don't think that works. Oh well. So there would be the histogram. It's not a perfect picture, but it's mine. So if we wanted to, down here is the R code for constructing a histogram. So the R function is hist, and I've given it some parameters to manually specify the breaks because otherwise it would choose its own algorithm. It would use its own procedures to come up with the breaks. And I wanted to override that, and this is one way to do it, where I basically gave the function the break points. So the minimum of soccer is going to be 1. So 1 minus 0.5 will be why can't I do math? It's 0.5. And then I went 1 above the maximum score, so that would be this number right here. So this right here corresponds to 0.5, and this will be 9.5 over at the right hand side, and that's just telling it where I want those breaks, and then it will infer that that everything in between is a bin. But then you end up with a plot that is essentially what we came up with by hand. Okay. Next example for the data set in example 1, let's create a histogram. Okay, so for that one, I am going to use the relative frequencies instead. Which do you use? At this point, it doesn't really matter because the shape is going to be the same regardless of whether we divide by n or not. And the interesting part when you're creating a histogram is looking at the shape of the resulting histogram. So I actually really don't care, although, for what it's worth, if you wanted to use this thing for more probabilistic inference, you probably should pay more attention to whether you've got the frequency or the relative frequency. And if also the bins were not of equal length, then you would have to pay much more attention to the frequency versus relative frequency, but also just take my advice and make your bins all equal length. So we've got the relative frequency. That is what we're going to draw this time. And we've got the highest it will ever go is 0.5. In fact, I don't think it ever reaches there. So we've got, right, yeah, it does. It does reach 0.5. So, and we'll just increment by 0.1. So 0.1, 0.2, 0.3, 0.4, 0.5. So this is 0.1 right here. So possible bin values, I decided that we were going to have 5 bins for some crazy reason. I don't remember what it was. And so let's see. Is that 5? It is now. So we've got numbers between 5 and 6. And using the table that we came up with that time ago, we're going to end up with a histogram looking something like this. So it goes up to here. And then, so it goes to 0.2 and then 0.1 for these remaining bins. And that's our histogram. So if we were to continue along and look on the next page, I think that's the reason why I chose 0.5. It's because it's exactly what R thinks it should be. And you should given the choice between what you think the number of bins should be and what R thinks it should be, you should probably go with what R is doing. Don't fully trust it, but at this point you probably don't have the experience to have your own opinion. So, it came up with basically the same picture. Okay, now we've been coming up with these nice plots, and everything is great. 1 second, let's just satisfy my nervousness. Okay, we're still good. Okay, making these pictures is nice, but why are we making these pictures? Well, there are certain things that we are looking for when we're making visualizations like this. For example, is the data unimodal? One thing we're looking for is modality, which is where does the data tend to cluster? Is the data unimodal, where it only has one peak? This would suggest it's clustering around one area. Or on the other hand, is it bimodal or multimodal, where you have multiple peaks? So the unimodal case would be something that resembles this, so we'll call this unimodal. Bimodal would be a situation like this. Maybe think of it as a camel hump. And multimodal is like all Like you've got all sorts of different modes, all sorts of different peaks. So what would it mean if you had unimodal versus bimodal versus multimodal? For starters, the multimodal case, the first thing that you should ask with multimodal is, did I choose a bin that's too small? Because you can end up with situations, if you choose your bin size to be too large when you're making a histogram, at one extreme you can have a skyscraper where everything is in one bin, and that is a chart that doesn't really tell you anything. On the other hand, you could have that basically a pancake where every single observation gets its own bin, and that really doesn't tell you anything either. That's basically a dot chart, and you've kind of lost the point of a histogram. So the first thing in the case of this blue sort of histogram, it's not really a histogram because it's a smooth curve, but whatever. In this case, you should probably ask yourself whether you've chosen too few bins. It could happen that you have genuinely multimodal data, but the number of modes should not be too many, because modality and having more than one mode is indicative of there being more than one actual population in your data set. So, for example, if I say that this is tracking height of people, I could genuinely have a bimodal data set, because actually there isn't one population in this data set of people. There's actually two populations, men and women, because men and women will cluster around different average heights. So that's features that you're looking for. Unimodal indicates that your data set, it probably consists of one population. And another thing that we're looking for when looking at stuff like histograms, and by the way, a lot of this discussion also applies to the stem and leaf plot and the dot plot. In particular, the stem and leaf plot, because you can argue that the stem and leaf plot is actually a histogram. It's just a histogram with a particular bin choice, but there's nothing really different about it. But anyway, is the data positively skewed or negatively skewed or symmetric? So a positively skewed data set, the way I like to think of it is, well, let's first draw it out. We have the positively skewed data set, and then we have the negatively skewed data set, which looks more like this. And then we have the symmetric data set. Let's do a little bit better than that. Okay, that's a little bit more symmetric. Okay, so if you're at all bothered by the terms positively skewed, negatively skewed, symmetric, and you're wondering, how can I tell the difference between positively skewed and negatively skewed? Here's a little rule for you. Draw a dinosaur. Draw a dinosaur. And then ask, where is his tail pointing? In the case of the black dinosaur, it's pointing towards the positive end, so it's positively skewed. All right, now let's talk about the green dinosaur. Well, let's draw the green dinosaur. Give him some legs. Give him some stuff on his back, because it's like a stegosaurus, so he's got these plates on his back. Where is his tail pointing? Oh, it's pointing in the negative direction, so it's negatively skewed. Right, and you don't draw a dinosaur for symmetric, because I don't know, we're just not going to do that. We're already silly enough. But why does it matter whether a data set is positively skewed or negatively skewed? It matters when we're thinking about the relationship between important statistics such as the mean and the median. So the mean and the median are going to behave a certain way and have certain relationships depending on whether the data is positively skewed or negatively skewed. Positively skewed data sets, what that basically means is that there are outliers in this data set, and when observations tend to be large, they tend to be very large. Negatively skewed data sets are data sets where when an observation is small, it tends to be very small. And I can think of specific data sets that fall into these types of categories. Like, for example, income tends to be positively skewed. So you have most people in a certain range of incomes, and then you have a few people who make much, much more than that, right? So most people are around here, but when you're rich, you tend to be very rich. And on the other hand, for negatively skewed data sets, I do have something in mind. I have test scores. Test scores for me, like there's a lot of ways test scores could actually appear statistically, but it seems like most students tend to fall within a certain range, and the students who really didn't get it, when they fail hard. So it tends to be negatively skewed. And symmetric, symmetric is kind of this ideal case where you're just as equally likely to be above or below. I think heights could be possibly. I haven't really looked at a height distribution in a long time, but I think that heights could probably be symmetric, where it's like you're just as likely to be really tall or really short at some degree. So you're also looking in these plots for outliers. For example, a histogram that has an outlier. You might have a histogram that looks something like this, and then you have a point that's way out here. And you would say that this point right here is a candidate to be an outlier. And you're also interested in how spread out the data is. And by spread, when we're talking about spread, we're talking about the less spread out black distribution as opposed to the more spread out green distribution. Which of these cases are you actually looking at? Or at the very least, you're just interested in what the range of the data is. Okay, so that's it for visualizing quantitative data. Now let's talk about qualitative or categorical data. How do you visualize that? We're only going to advocate one method here, and that's a bar plot. In fact, in my visualization class, I was told if you don't know what visualization method to use a bar plot. Because bar plots are actually very good visualizations. Never, ever, for the love of God, draw a pie chart. I know, especially in like public policy and economics, people love their pie charts. For the love of God, do not create a pie chart. Do you have any idea how many memes of ugly and stupid pie charts there are? Please do not draw a pie chart. Okay, continuing on. To construct a bar plot, list each possible value of the variable and how frequently that value is taken. A lot like what we were doing before, it's just instead of having numbers on the left-hand side for like these bins, instead of that, you're just going to have the categories that your data set could be in. And then you're going to draw a horizontal line. So let's see, a cartoon bar plot that we're making. So we have like category A, category B, category C. So draw a horizontal line. It could be a vertical line. It doesn't really matter. And along the axis marks possible values of the variables, and then draw a bar for each category extending to the category's observed frequency. So we'd end up with something that looks like this. It is worth mentioning, bar plots and histograms are two different things. And the difference is this axis here, this x-axis. With a histogram, that axis is a number line. And there is a very specific order. And if you were to plot a point on that line, it would mean something. Whereas with a bar plot, this doesn't mean anything. You could rearrange it if you wanted to, and the bar plot would say exactly the same thing. Even in the case of ordinal data, you could space it out. There's all sorts of transformations that you could do, and the plot says the exact same thing. That is not the case for histograms. So bar plots and histograms, despite looking somewhat similar, are certainly not the same thing. Okay, so for our next example, there is a data set showing the frequency of the class of passengers aboard the Titanic who survived her sinking. I have the Titanic data set in R. Contains this data set, but they're actually tracking a lot of things. They don't just track the class, they track male and female, they track age, they track survival, and so on. Here I have restricted to using this apply function, which I'm not going to talk about right now. I have restricted it to the case of survivors for certain classes. I want to create a bar plot for the frequency of each class's survival. So I've already got the frequency distribution. R has already given it to me very nicely. So I'm going to say we've got first class, second class, third class, and crew. Okay, and then we're going to extend up. We're going to say up here, let's say that this is 220. And right here, we've got 110. We're going to just eyeball this. So for first class, there were about 203 survivors, so that's about here. For crew, there were 212 survivors, so that's about here. For second class, there were about 118 survivors, that's about here. For third class, about 178. So our bar plot should look something like this. Okay. And in fact, we can look at what R does. We give the bar plot function in R this data set, and it will in fact make a very nice bar plot for us. Okay. There is actually a visualization method that I haven't really discussed here, and I'm making a video. Everything's quite nice. I really don't see why I shouldn't show you this if you're familiar with R. So let's see. First, are we still streaming? Yes, we are. Okay, so there is another type of visualization called a density plot. You cannot make a density plot by hand. So I'm going to go ahead and I'm going to make a density plot. Does this command still work? This is a new installation. Oh, good. Everything's working. Maybe we should go back to... let's see. What's a data set that we could work with? Rivers is fine. This is the length of some North American rivers. And there is a plot called a density plot. Remember that I was drawing some smooth curves? And histograms do not look like smooth curves. What I kind of was drawing was a density plot. So I could create such a plot by typing in plot, density, and then give it the name of the data set if it's stored in a vector. So in this case, rivers. And this is the resulting density plot. And it's actually plotting a smooth curve. Let's see. What's one of the data sets that we were looking at before? Page up. What data set was this? Okay, so we had this height data set. So let's go ahead and combine those two things. Center on this. Okay, so height will be a vector consisting of the numbers 5.55, 5.30, 5.03, 5.30, 5.13, 5.05. What was that number? 5.36? No, that's 5.38. So we've got 5.38, 5.96, and 5.21, and 5.38. Okay, so here's our data set. And I'm just going to create a density plot for this data set. That's not it. It's still rivers. Oh, because I typed in rivers. Silly me. Okay, so what I want instead is height. There, that's better. And it makes a smooth curve that kind of resembles... Actually, it certainly does resemble the histogram that we drew. Except it's actually, like in the histogram, there is, in fact, when you look at that data set, kind of a peak in this region. And that was completely masked by the histogram. But the density plot was able to capture it. Interesting. So, but you have to make a plot like this in R. You cannot make a plot like this by hand. So, I'm just bringing it to your attention because these kind of plots do show up. All right, so that's it for section 2 of the book. And I thank you for joining me. And I will see, and I hope that you watch the video for section 3. So have a nice day.